Hello and welcome back once again to C++ Real-Time Audio Programming with Bela. We've been going over the building blocks of synths and audio effects in the C++ programming language, and today we're going to start looking at one of the most fundamental protocols used to control synthesizers, and this is, of course, the MIDI protocol. In this lecture, we'll introduce the MIDI protocol and its main types of messages. We'll look specifically at how to handle note-on and note-off messages sent from a keyboard or other controller. We'll also look at how to keep track of multiple notes at once. This is the first lecture of a two-part series on the MIDI protocol. This time we're going to look only at the note-on and note-off messages. In the next lecture, we'll expand our vocabulary to include the pitch and modulation wheels and control change messages. By the end of this lecture, we'll make a monophonic MIDI synth which uses an ADSR or attack decay sustain release envelope. As always, the companion materials, including code examples and extra reading suggestions, are available at the GitHub link at the bottom of the screen. For this lecture, as usual, you'll need a Bela starter kit or a Bela mini starter kit to run the code. This time, we also suggest that you use an external MIDI keyboard plugged into the Bela board. If you don't have a MIDI keyboard, you can also use virtual MIDI keyboard software, which will send MIDI messages from your computer over the USB link to the Bela board. Two programs that we suggest are MIDI Keys, which runs on Mac, or VMPK, which stands for Virtual MIDI Piano Keyboard, which is an open source cross-platform program. Links to these programs can be found in the companion materials. Okay, to begin, what do we mean by MIDI? MIDI stands for Musical Instrument Digital Interface, and it's by far the most common industry standard for communicating amongst digital music devices. MIDI has been in use for quite a long time, having been introduced back in 1983. It's maintained by a group called the MIDI Manufacturers Association, and you can find more information on the specification at their website, midi.org. MIDI messages are typically sent over one of several different transport layers. The traditional and original way of sending MIDI messages is over a 5-pin DIN cable between devices. This is a serial link which goes in one direction only, running at around 31 kilobits per second. More commonly these days, MIDI messages are sent over USB cables or Bluetooth connections. It's also possible to make virtual MIDI ports between software applications running on a computer. Regardless of which kind of transport you use, the format of the MIDI data is the same. The fundamental unit of MIDI is known as the message. A single MIDI message consists of a discrete packet of between 1 and 3 bytes of data. These messages are sent one after another over the transport, without any particular signposting between them. Therefore, the challenge with MIDI is understanding when one message ends and the next message begins. In other words, if we were to read our serial port, we would read a continuous stream of bytes, and this is the only information we have. Our challenge is to figure out which bytes group together into MIDI messages. MIDI provides a very simple solution to this, which is that the first byte of every message always has its high bit set to 1, and every other byte of a MIDI message has its high bit set to 0. Recall that a byte consists of 8 bits, which can represent numbers between 0 and 255. Therefore, a byte with the top bit set to 1 will have a value of 128 or higher, and a byte with the top bit set to 0 will have a value of 127 or less. The first byte of each MIDI message, which has its top bit set to 1, is known by convention as the status byte. The other 7 bits of the byte will tell us what kind of MIDI message it is, and we'll get back to this in a second. The remaining bytes in the MIDI message are called the data bytes. The high bit of these bytes has to be set to 0, and the data is stored in the other 7 bits. You can see that because the top bit is always reserved to tell us whether a byte is a status byte or a data byte, that MIDI messages effectively have 7-bit resolution because there's only 7 bits left over to hold the data. The MIDI specification is available online, and it contains a complete rundown of all the possible MIDI messages and the meaning of the data. We're going to look at a few of the most common MIDI messages in a moment, but before I get there, I want to preface this discussion with a few of the musical assumptions that go into the MIDI protocol, which might have subtle biases on the way that we think about representing music. The MIDI protocol was designed in the 1980s first and foremost to represent Western traditional music, and especially music performed on the keyboard. Therefore, MIDI makes quite a number of assumptions about music that make good sense when dealing with the keyboard, but potentially less sense when dealing with other kinds of instruments. For example, MIDI proposes that the fundamental unit of music is the note. A note is characterized by a discrete instantaneous onset time and a discrete instantaneous release time. For this reason, we'll sometimes hear people talk about creating MIDI events as triggering notes. MIDI represents note onset events as a message containing a note number and a velocity. The term velocity itself brings to mind the acoustic piano, because the analogy is the speed of a key press. The general assumption in MIDI is that the velocity of a note corresponds to its volume, although it doesn't have to be implemented this way. Likewise, note release messages are also characterized by a note number and a velocity. The idea is that the velocity of note release may have something to do with the speed of the key release motion. In practice, many MIDI keyboards don't implement note release velocity, and many synths don't use it. As we just saw, each MIDI note message is also characterized by a note number. We saw before that most MIDI data is represented by 7 bits, and so there are 2 to the 7th or 128 possible note numbers, numbered between 0 and 127. By convention, these 128 note numbers correspond to keys on the traditional keyboard, with the convention that middle C always has MIDI note number 60. That means that if you have an 88-key grand piano, the note numbers will range between 21 and 108. Notice the assumptions here. The note numbers are organized sequentially by piano key, which means that there are always 12 note numbers to the octave. MIDI note-on and note-off messages are discrete, but there are other types of MIDI messages which can provide a more continuous control over the sound. Here, too, there are a number of musical assumptions that went into the design of these messages. Particularly, these messages are designed around the interfaces and capabilities of electronic synths. For example, we can talk about control change messages, which typically correspond to the knobs on the front panel of a synth, which we might turn. My point in discussing these assumptions is to highlight the fact that there are many possible ways of making music, and that it's very easy to fall into the assumption that MIDI is a universal standard for all types of music, when in fact it's particularly suitable for keyboards and for Western staff notation. It's a tremendously versatile protocol, but as an instrument designer, it's useful to be aware of its biases. Let's now talk about the particular kinds of MIDI messages we might encounter. As we discussed, the first byte, or status byte, tells us what kind of message it is. Specifically, most but not all types of status bytes are broken into 2 4-bit segments. The high 4 bits will tell us what kind of message we're dealing with, and the low 4 bits will tell us which MIDI channel the message is designed to affect. 2 to the power of 4 is equal to 16, and so a MIDI message can affect one of 16 channels on the same MIDI cable. The original use of this capability was to control multiple different instruments with the same MIDI cable using different MIDI channels. A single MIDI channel could have any number of notes active simultaneously, but most types of controls, such as control change or pitch wheel messages, are going to affect all the notes on that channel. There are more recent extensions to the MIDI spec, such as MPE, which use these 16 channels for 16 different notes, each of which gets its own independent controls. We're not going to talk about that more in this lecture, but I'll include some details in the companion materials. If you're using MIDI hardware or software, you'll typically see the channels numbered between 1 and 16. In actual implementation, the low 4 bits of the status byte will have the channels numbered between 0 and 15. In other words, what the user of a synth would call MIDI channel 1 is actually a value of 0 in the low 4 bits of the status byte. Let's now look at a few specific types of messages. First of all, the note-on message. The note-on message always begins with a status byte which has the value 1001, or 9, in the top 4 bits of the byte. This status byte is followed by 2 data bytes. The first of these holds the 7-bit note number, and the second of these holds the 7-bit velocity. Again, these both have values between 0 and 127. A very common convention with MIDI is to use a note-on message with a velocity of 0 to actually mean note-off. However, there is also a separate MIDI note-off message. This begins with a status byte that has the top 4 bits equal to 1000, or 8. The note-off message has a 7-bit note number and a 7-bit velocity as data bytes. In practice, any given MIDI keyboard will usually send note-offs in one format or the other, either note-on with a velocity of 0 or with actual note-off messages. You'll also commonly see MIDI control change messages. These start with a status byte whose top 4 bits are 1011. This corresponds to a value of 11, or in base 16 hexadecimal, a value of B. I'm not going to talk about hexadecimal here, but I'll put some information in the companion materials. The control change message has 2 data bytes. The first of them is the controller number, which again is between 0 and 127. That's followed by the value of the controller, which also ranges between 0 and 127. MIDI uses control change messages for all sorts of things. That includes dials and sliders, also pedals, breath controllers, and the modulation wheel. The MIDI specification also defines some standard controller numbers for different types of controls. For example, the mod wheel is always controller 1. Controller 7 is defined to be volume, controller 11 is defined to be expression, 64 is the damper or sustain pedal, etc. Some controller numbers are instead reserved for special functions. For example, controller 123 means all notes off. Whenever a control change message is sent with this controller number, the expectation is that the synth will cease sounding any of the notes that are currently playing. The MIDI specification contains more complete details on the meaning of each controller. Other messages you're likely to encounter include the program change, which is designed to switch between different types of sounds on a MIDI synth. Program change messages have a status byte that begins with 1100, which is a value of 12, or hexadecimal C. The program change message only has 1 data byte rather than 2, and this indicates which program number should be selected. The specification known as General MIDI, which extends the MIDI 1.0 spec, defines particular instrumental sounds for each program number. For example, sound number 1 is a grand piano. Again, you can find more information about this specification online. Another common message is channel pressure, more commonly known as aftertouch. Here, the status byte begins with 1101, which is a value of 13, or hexadecimal D. Channel pressure messages are typically generated by MIDI keyboards, which have a pressure sensor underneath the keys. It's possible that other types of MIDI controllers besides keyboards would also generate channel pressure messages. A notable feature of the channel pressure message is that it affects all the notes on the channel. Typically, it's from a sensor which goes underneath all the keys, rather than being a note-by-note measurement of key pressure. Therefore, the channel pressure message only has 1 data byte, which is the value of the pressure, again ranging from 0 to 127. The pitch wheel message is another commonly encountered one. Pitch wheel is a special kind of control in the MIDI specification because it has a 14-bit resolution rather than 7 bits like most MIDI control changes. The pitch wheel message has a status byte beginning with a binary value 1110 or 14 hexadecimal E, followed by 2 data bytes holding the 14 bits of value. Notice these bytes are organized with the least significant bits coming first. 14-bit resolution translates to 2 to the 14th or 16,384 possible values. By convention, the center value of the pitch wheel is a value of 8,192. This corresponds to no pitch bend either up or down. A higher value will correspond to a pitch bend up and a lower value to a pitch bend down. By convention, the pitch wheel range corresponds to plus or minus 2 semitones. However, different synths can implement different ranges, and there is in fact a special series of control change messages which can adjust the pitch wheel range. The final types of messages that you'll encounter are polyphonic aftertouch, which is essentially like channel pressure but is specific to each individual key. Polyphonic aftertouch has a status byte beginning with 1010 or 10 hexadecimal A, and has 2 data bytes, 1 for the note number and 1 for the aftertouch value. Other messages that are not channel specific include system real-time and system exclusive or SysEx messages. Each of these messages begins with 1111 or 15 hexadecimal F. System real-time messages are used for controlling various transport and timing functions of a synth, whereas system exclusive messages are designed for transporting manufacturer-specific data. SysEx messages have a variable length and are encapsulated by a hex value of F0 at the beginning and F7 at the end. Within that, there will typically be a code indicating what manufacturer the message is designed for, followed by manufacturer-specific data. So that's an overview of the types of MIDI messages we'll encounter. Again, for this lecture, we're going to focus on note-on and note-off messages. More generally, though, it's worth thinking about how MIDI and audio interact. Recall that digital audio is a sampled signal which has a constant sample rate and, in typical real-time implementations, a regular block size. By contrast, MIDI messages are sporadic events that might come in at any time, with no particular guarantee on how it aligns to the audio frames. The only thing we really know is that the MIDI messages are always going to come in sequential order, which is to say that one message will finish before the next one will begin. This sets up a familiar problem, which we last saw in Lecture 10. That problem is jitter. The problem that we'll have is that the latency in responding to any given MIDI message might vary randomly depending on when that message happened to arrive relative to the audio block. MIDI note messages are coming in from a different hardware device than the audio device in a completely different thread. They might arrive at the beginning of a block, in the middle of a block, at the end of a block, but in the simplest implementations, the soonest you'll be able to respond to that MIDI message is at the beginning of the next block. Therefore, the amount of delay between receiving the message and having its audio response will vary. One way around this problem is to include some sort of strong timestamping on the MIDI messages themselves, where the operating system records very precisely exactly when the message came in, and then the synth can choose to respond to it at a constant delay rather than a variable one. We're not going to look into that in this lecture. Specifically on Bela, MIDI is implemented using the standard Linux drivers called ALSA. This means that support for MIDI devices is provided by the Linux kernel. The advantage of this is that it's widely compatible. Any MIDI device that will work on Linux will work on Bela, and oftentimes they're just simply plug and play. It also means that all sources of MIDI data will appear equivalently to the Bela program, whether that's coming from a serial MIDI port, a USB port, or software virtual ports, as long as they're supported by ALSA. The disadvantage is that the ALSA MIDI system is not a hard real-time task like the Bela audio task is. That means we don't have the same degree of high priority for MIDI messages as we do for audio, and in principle, if the system load went up, we might start to see delays in the MIDI messages. In practice, although there aren't any latency guarantees on MIDI messages, my experience is that the latency tends to be quite low. We're getting toward our first MIDI example program on Bela, so let's look at the ways that we might connect MIDI devices to the board. The first way that we could do this is to connect a hardware MIDI device, typically by the USB host port on the Bela or Bela Mini. We could also have Bela be a virtual MIDI device to communicate back and forth with the computer. What this means is that when Bela is plugged in, it will show up to the computer as a MIDI source and destination, and likewise your Bela program will see the computer as a possible source and destination for MIDI messages. This means that we can exchange MIDI back and forth without any physical cables other than the USB cable already used to plug in the Bela board. The way we choose which device to use is to specify a device name. The device name is a specially formatted string whose meaning is given by the ALSA system. Typically, the virtual link to the computer is HW:0,0,0, whereas the first device connected by USB is HW:1,0,0. You can always see what devices are connected to your Bela board by running the command amidi-l in the command line terminal at the bottom of the IDE. So let's plug in a device now and see how this works. Here I have my Bela board. I'll connect the USB cable to the host port, and then I'll connect it to the MIDI keyboard. We can see that the keyboard is powered by the Bela board. And now here we are in the Bela IDE. We just need to go down to the terminal at the bottom of the screen and we type amidi-l. And this will give us the devices currently connected. So the first one there corresponds to the virtual port, and the second one to the keyboard I have plugged in. You notice here that there's only 2 zeros and not 3 as in the slides. The third number would be used for selecting between different MIDI ports on the same device, but since each of these devices has only one port, it doesn't really matter whether we include that or not. Now let's see what we need to do in our Bela program to use MIDI data. Bela provides a relatively straightforward API that wraps the ALSA Linux system. To use it, you need a few things. First of all, you need to include the library called midi.h. Second, you're going to need to make a global variable of type MIDI. This is going to handle the communication to and from the MIDI device. Third, you'll need to initialize the MIDI object inside of setup. This is the place that you'll tell it which MIDI port to read from or to write to. The third line here, calling a method enable parser, is needed to get the MIDI messages from the device within the render function. Then reading and writing messages can be done inside of your render function here. You can see that at the top of the render function we have written a while loop. The while loop runs as long as the condition is true, and what we're doing is we're checking whether there have been any new messages received. If there are messages received, then we can get it from the parser using the method getNextChannelMessage. We can then decode the message according to what type of message it is. This involves a series of if statements. The types are defined inside the midi.h file. For example, kmmNoteOn indicates a MIDI note on message. There's a lot more detail about the Bela MIDI API inside of the IDE. In the Bela examples in the communications folder, you can see an example called MIDI, which shows a few more options that you can use with the MIDI library. You can also go here to the libraries in the Bela IDE, and you can see the MIDI library has several examples that you can look at. There's a few other considerations before we move forward. I've said it a couple times already, but it's worth reiterating that the MIDI messages are fundamentally asynchronous with the audio. We have no guarantee about when these messages come in with respect to the audio blocks. That means whenever you're reading MIDI messages inside of your render function, you're going to see all the messages that arrived since the beginning of the last block, and you won't necessarily know exactly when in the block the message was received. Another important quality of a MIDI message is that its effect should be persistent. That means that when a message comes in, we should oftentimes start doing something and continue doing it until we receive another message to tell us otherwise. As an example, when we get a note on message, the synth should start playing sound, and it should continue playing sound until a note off message occurs. Similarly, a control change, pitch wheel, or channel pressure message should continue to maintain that value until a different message is received. This implies that when we deal with MIDI, we always need to be remembering what has happened before. And the easiest way of doing that is to use global variables to keep track of what's going on. For example, we might have global variables to tell us which notes are sounding at any given time, or what the value of the controls or pitch wheel would be. To make this more specific, when we get a note on message, what we should do first is to start generating sound for that note. If the sound has a continuous sustain, we should keep generating it until we get the note off message. However, if the sound has a fixed length, for example percussion, then we might generate it for a fixed length of time and not worry about the note off message. We're also going to need to look at the note number that comes in and use that to determine the frequency of our synth. We might also use the velocity of the note on message to control the amplitude or possibly the timbre of the sound that we're generating. Not all synths necessarily need to use the velocity number. Classic analog synths, for example, didn't have velocity-sensitive keyboards. We then need to wait for a note off message to arrive for the same note number. At that point, we should stop generating sound for that particular note. We're going to look a little bit later on at how we handle multiple notes being on simultaneously, whether our synth is monophonic or polyphonic. To work out how to generate the frequency of a sound based on the note number, let's review an earlier lecture. Remember that human pitch perception is logarithmic, and that musical intervals are defined as ratios of frequencies rather than constant differences between frequency. For example, an octave is always a 2-to-1 ratio of frequency. Therefore, to get from frequency to notes on a keyboard, we need to have a calculation involving a logarithm, or the other way around, to get from keyboard notes to frequency, we're going to need to have an exponential function. Remember that the MIDI keyboard has the A above middle C defined to have a frequency of 440 Hz. That means that one octave higher than that is 880 Hz. The difference between these is 12 semitones or 12 keys. Here's a plot of the frequency with respect to the MIDI note number. Remember that middle C on the MIDI keyboard is always MIDI note number 60, and therefore the A above middle C is MIDI note number 69. When we first looked at converting from note number to frequency, we were looking at this in the context of analog control voltages. We saw a common linearized scale of 1 volt per octave, where each additional 1 volt of CV caused the frequency to double. What this let us do was calculate the output frequency as a function of a reference frequency and some number of volts, V. However, remember that if V was measured in semitones rather than in octaves, we would instead have a slightly different formula. We had to convert the number of semitones into the number of octaves. The way that we did that, of course, was to divide by 12. So here we ended up with a formula where the frequency of our note was defined as a reference frequency times 2 to the power of V over 12, where V is the number of semitones. This was what we needed to work out how to turn MIDI note numbers into frequency. By convention, middle C is MIDI note number 60, and the A above middle C is MIDI note number 69. That A has a frequency of 440 Hz, which let us write a formula to go from MIDI note number to frequency. What we needed to do was calculate the number of semitones above or below A440. For a note number n, the way that we would do this was to take the value n minus 69. Next, we needed to know how to convert that into a number of octaves. The answer here is to divide that by 12. So n minus 69 divided by 12 tells us how many octaves above or below A440 our note is. Then we have a correspondence between note 69 and 440 Hz, which let us write the formula like this. So the frequency is given by 440 times 2 to the power of the note number minus 69 divided by 12. This brings us to our first task. In the companion materials, you'll find an example called MIDI sine tone. This, when completed, will give you a sine wave synth controlled by a MIDI keyboard. However, before implementing any of these coding tasks, it's worth simply running this example to make sure that you have communication between your MIDI device and Bela. Going over to the IDE now, I have the example open and I have a MIDI keyboard connected. I haven't made any changes to the code yet. Down here we have the name of the MIDI port that the project will use. As we saw before, HW:1,0,0 is your typical name for the first USB device plugged into the Bela board. If you want to use the virtual MIDI port from the computer, then you can use HW000 instead. Let's just run this project and make sure that we're getting MIDI messages from the keyboard. Now you can hear that once we pressed the first key, a sine wave started which doesn't stop. That's because we haven't finished implementing this project yet. Let's also just check that the wheels work. Here's the pitch wheel, and also some of the other controls. Okay, back to the coding task then. There are 3 things you need to do. The first is that you need to implement the conversion between MIDI note number and frequency. This will happen inside of the function called note on. The second thing you need to do is you need the sound to stop when a note off message is released. This requires you to add some code inside the function called note off. Finally, use the velocity value of the MIDI note on message to control the amplitude of the oscillator. I suggest that you map this in a logarithmic capacity using a decibel scale. Decibel scales were covered in Lecture 4. We came up with these formulas to convert between linear and decibel scales of amplitude. My suggestion is that you map velocity values 1 to 127 to an amplitude range of minus 40 dB to 0 dB. However, you can experiment with different values. Remember again that a velocity value of 0, when received with a note on message, actually corresponds to a note off message, and the note off function should be called instead of note on. So that's what you need to do. When you run the program, you should find that the sine wave generator responds to your key presses, and that when you release the key, the sound goes off. If you hold down multiple keys at the same time, you might find some slightly unexpected behavior, which we'll come back to. But for now, pause the video here and implement these things. Okay, here's the completed MIDI sine tone example. As before, we're using an external USB keyboard to control the project. What you needed to implement was inside the functions called note on and note off, so let's start there. The note on function is going to be called from render whenever it receives a MIDI note on message. You can see that it has 2 arguments. One is the note number, one is the velocity, corresponding to those 2 fields in the MIDI message. What we need to do is first map the note number to a frequency. Here we see the implementation of the formula we saw on the slides. If you've been following the lecture series straight through to now, then this formula should be familiar already. We then need to map the velocity to a decibel scale. Again, this should be familiar if you've been following the lectures continuously up till now. We're starting with a function called map, which produces a linear rescaling of a value. So we pass in the velocity number and we rescale it from the range 1 to 127, which is the range of possible MIDI velocities, to the range minus 40 to 0, which is the range in decibels. Now before we can go any further, we need to convert decibels into linear amplitude, which we're going to do according to the following formula, which implements what we saw on the slides. Frequency and amplitude are then stored in 2 global variables, G frequency and G amplitude. The idea is that these are now remembered for future calls to render. The last thing we do is we set this flag called G is note on. This is defined up here at the top of the file like the other ones, and notice that it's of type bool, which means that it only holds values true or false. This is just telling us, is our synth running right now? So we set it there to a value of true, which says that the sound should be generated. Now that last line also gives you an idea of what you need to do inside of note off. To make the sound stop when we release a key, all we need to do is set G is note on to be equal to false. What that means is that inside of the render function now, our oscillator will no longer run. And let's look at that now. Initially, I'm going to skip over the MIDI message parsing just to see how the synth itself runs. Here we have our usual for loop, which goes through the number of audio frames, and we have this if statement that checks whether the note is on or not. If that's the case, then we do our usual sine wave calculation, which was covered in the earliest lectures of this series. You can see that it takes G frequency and G amplitude as part of its calculations. That's written to the audio output channels when we're done. Finally then, we'll go have a look at the MIDI message parsing. We're using the version of the Bela MIDI API where we query whether any new messages are available. We call gmidi.getParser. That gives us an object that we can call another method from called numAvailableMessages. That tells us the number of messages that are available for us to parse. If there are any messages available, then we're going to get the next one. We're going to define an object of the special type MIDI channel message, and then we're going to call this method here to get it from the parser. This line here is responsible for printing the contents of the message to the terminal. It's useful for debugging, but you can turn it off if you don't want it. Then what we need to do is check what type of message we have. The object MIDI channel message has a method called getType. This will tell us which of the types of messages we have. It might be a note-on message, for example, or it might be a note-off message. We could likewise extend this to include control change messages, program change messages, pitch wheel, etc. But once we know what type of message it is, then we need to get the data from it. So given a note-on message, we're going to get the note number, which is the first data byte, and the velocity, which is the second data byte. Remember that a velocity of 0 is actually a note off and not a note on, so we have to check for that specially here. Otherwise, we're going to call the function noteOn, and we're going to pass it those two arguments. We also print here to the terminal. You can see here we're using the function rt_printf. If you're ever going to print to the console in Bela's render function, you should always use rt_printf and not the regular printf function, or you might end up with mode switches. If we, on the other hand, got a note-off message, then we can get which note number it is from the first data byte. There is also a second data byte with a release velocity, but for this particular synth, we don't care about that, so we don't bother getting it. We just call the function noteOff and pass it the note number as an argument. So we can run this now and see how it works. And now we can hear it play a few keys and hear how it sounds. Now you might notice something kind of funny if you hold down multiple notes at a time. It will always remember the most recent note. But once you release any of these keys, the sound will stop. This, of course, is not how we would expect a synth to behave, and we need to look at it in more detail. Keyboard-based synths can be divided into two categories, monophonic and polyphonic. A monophonic synth is one which plays one note at a time, no matter how many keys have been pressed. Early analog synths were almost universally monophonic, the reason being that they only require one of each component, only one oscillator or VCO, only one amplitude controller VCA, and only one filter or VCF, etc. Of course, it's possible to build a more complex monophonic synth with multiple oscillators, multiple filters, etc., but the number of components required doesn't scale with the number of keys pressed. By contrast, a polyphonic synth will be able to play multiple notes at a time. This, of course, is how the piano works. To make a polyphonic synthesizer, each note is going to need to have its own independent oscillators, filters, and amplitude controls. A typical polyphonic synth might have some maximum number of simultaneous notes to limit the amount of hardware or CPU required. For example, it might play only 8, 16, or 32 notes at a time. It's possible to build polyphonic analog synths, for example the famous Yamaha CS80, and digital and software synths are quite often polyphonic. In this lecture, we're going to make a monophonic synth, or monosynth for short. It seems like an easy task because we only have to play one note at a time. However, the challenge is, which note should we play? Remember that the MIDI keyboard might still generate multiple note-on and note-off messages. The typical behavior of a monosynth will be to play the most recent note it has received, and indeed that's what we did in our example. The problem starts when we have multiple notes active at a time and one of the notes goes off. In the example we just saw, the synth went silent, which wasn't what we want. What we actually want is for the synth to revert to an earlier note that's still being held down. The problem here is that we need to remember not only the most recent key that's been pressed, but all the key presses that are currently active in order of arrival. By doing this, when the most recent note goes off, then we can go back to whatever the most recent one before that was, and then only when all the notes have released should the synth go silent. How do we do this? Well, we're going to need two things to remember multiple key presses. First, we're going to need an array which keeps track of the currently active notes. Now, by having this array, it doesn't necessarily mean that we have a polyphonic synth. We might only still have one oscillator, one filter, etc. It just tells us that we're remembering which keys were held down. The way we'll order this array is to have the oldest notes occupy the earliest slots. We'll also need some kind of counter to keep track of how many notes there are in the array at this moment. The counter then also doubles as a pointer to the first empty slot in the array. In this example, we're starting with 3 keys held down. MIDI note numbers 60, 57, and 55 pressed in that order. Therefore, the note count is 3. Suppose that we receive a note on message with a note number of 64. Now what we need to do is add this note number into the array at the pointer location. So the 4th slot in the array will now acquire a value of 64. The next thing we need to do is increment the counter so that it points to the next available empty slot. Finally, we can now start the note as we did before, setting its frequency, starting any envelopes, etc. Starting the synthesis is actually going to be no different than what we did before. The reason that we're keeping track of all these active notes is that we want to use them when we receive a note off message. So now suppose that we received a note off message for note number 64. What we need to do is we need to step through each of the notes in the array to see if it matches that particular note number. So we're going to write a for loop of some variety which checks each of these slots and asks whether it has a value of 64. When we find a match, if that match is the most recent note that has been pressed, then we remove it from the array, we decrease the total count of active notes, and then we're going to tell the synth to play the previous most recent note. In this case, the oscillator will change to play MIDI note number 55 rather than 64. It's typical behavior on a lot of synths that removing a note in this way will change the oscillator frequency but not re-trigger the envelope. Suppose, on the other hand, that we received a note off message and it was not the most recent note, say the note number 57. Again, we're going to step through the array and see if any of these elements match that note number. We'll find a match here, and what we're going to need to do is again remove this note from the array. Now what we need to do is shift all the later elements of the array back so that the array is still contiguous. When we're done with that, we can decrease the total count of active notes. Now, since that was not the most recent note that had been removed, the synth doesn't actually sound any different at this point. It's still playing the most recent note, which is 64. However, if the array eventually became empty and the count was equal to 0, then we should turn the oscillator back off. This brings us to the next task. In the companion materials, there's an example called MIDI multinote. This is an extension of the sine tone synth, which is designed to keep track of multiple key presses at once. The code inside of note on is already written for you to keep track of the key presses inside of an array. Your job is to implement the note off function. You're going to need to implement the situations we just looked at so that when you receive a note off message, you check if it matches anything in the array, and then you remove it from the array, possibly updating which note is sounding. All the variables you need to do this are already declared for you at the top of the file, so have a look there. Once you finish this, you should find that it behaves much more as you'd expect a monosynth to behave. Pause the video here and try it. So here we are with the finished version of the MIDI multinote example. As before, we are using the hardware 100 input, which corresponds to the USB MIDI keyboard, which is connected. A lot of this code is very similar to the previous example that we worked with, except that now we're keeping track of multiple key presses. We have this array called G-active notes, and it can hold up to 16 elements, so we can keep track of up to 16 key presses at a time. In principle, there's no reason that this number couldn't be considerably greater. And then we have G-active note count, which indicates how many notes are being held down at the current moment. Setup is largely the same as before. We'll skip over that now. The note on function was already given to you. Here we see that every time a new note was played, we're going to store it into the G-active notes array at the point indicated by G-active note count. Then we increment the count so that the next time around we store it in the next slot. We have this if statement here just to make sure that if we get more than 16 notes at a time that we don't run off the end of the array. Things that we see here in terms of mapping the frequency and amplitude are exactly the same as they were before. Your job was to implement the note off function, so let's look at that. We'll start out with this flag called active note changed. We're going to update this from false to true if it turns out that the most recent note has gone off, and then we'll use the value of this flag at the end of the function. The core part of this function is given in this for loop. This for loop is counting from the end of the array back to the beginning. So notice that the index I starts at gActiveNoteCount minus 1. That is the last slot in the array that has a valid value stored in it. And this is going to decrease each iteration of the loop until we end up with a value that is less than 0. Inside the for loop then, we'll check each element of the array. If that element of the array matches the note number that's turning off, then we found a match. If we found a match, then we're going to need to remove it from the array, but first of all, we're going to need to figure out, is it the most recent note that has just gone off? So here we check if the value of I is equal to gActiveNoteCount minus 1, which is to say, if we are on the last slot of the array. If we are in the very last slot of the array, then it's the last note that's going off, in which case we should set ActiveNoteChange to true. The reason that we do that is that we're going to update the pitch at the end of this function. Then, regardless of that, we'll move all of the items back in the array to earlier slots. So you can see here we have a for loop inside a for loop. What we're doing is we're starting this value j at the index I. In other words, we're starting out at the slot in the array where we found the match. We're going to move forward from there to the end of the array, and what we're going to do is we're going to move each value back one slot in the array. This is essentially implementing what we saw on the slides, where we found an item we wanted to remove from the array, so we moved all the later items in the array back one slot. This is also fairly similar to what we were dealing with keeping track of previous state when we were looking at filters. Then the last thing we do once we find a match is decrease the number of active notes by 1. Once we get to the end of the for loop, then the matching note will have been removed from the array. Then we can check for a couple things. First, we check whether any notes are still sounding. If the number of active notes is now equal to 0, then the last note has gone off. We should set the amplitude to 0 and we can turn the note off. Otherwise, if the active note has changed, then we need to update the frequency according to the new, most recent note. That's this line of code here. We're going to get the MIDI note number of the last item that is still remaining inside of the array, and then we're going to convert it to a frequency just as we did before. Now, I'm not saving the velocity of each of the notes, so the amplitude isn't going to change in this case. We can here also print that the note has changed and what the new frequency will be. The contents of render are going to be largely the same as before, so we don't really need to go over them. Notice that we're calling either note on or note off, depending on what kind of MIDI message was received. And then I'm gating the oscillator depending on whether the active note count is greater than 0 or not. So if there's 0 active notes, then the oscillator isn't going to run. Otherwise, it will run, and it will be multiplied by the amplitude here. Let's run this and see how it works. Now, initially, this should sound fairly similar to before. The difference comes when we hold multiple notes. So you can see that as I release the keys, it goes back to the most recent note. And so it also becomes possible to play trills in this way. So now watch, if I put multiple notes down, and I remove a note that was not the most recent note, you don't hear anything change, but when I remove the most recent note, now it snaps back to the earliest note. So there, we've solved our note order problem for a monosynth. In the last part of this lecture, let's now connect our MIDI keyboard to the ADSR envelopes that we worked on in the last lecture. In Lecture 14, we saw that the ADSR was a very commonly used envelope for musical synthesis. It has 4 segments: an attack segment, which rises from 0 up to a maximum value, a decay segment, which drops down to a sustain level between 0 and 1, a sustain segment that remains flat until a note off occurs, and then finally a release segment that drops back to 0 over some specified period of time. These segments could be either linear or exponential. In Lecture 14, we just controlled our ADSR from a simple button. In this lecture, we're going to control it from the MIDI keyboard. The main thing that we need to change is to deal with the MIDI note on and note off messages. In the simplest case, where we only press one key at a time, a MIDI note on message would cause the ADSR to go to the attack state, whereas the MIDI note off message would cause it to go to the release state. In actual practice, with multiple keys, we'll have to implement something similar to what we just saw. So this is your task. In the companion materials, there's a project called MIDI ADSR, which includes most of what we did at the end of Lecture 14. we actually had not one but two ADSR envelopes. One controls the amplitude of the sound and the other controls the cutoff frequency of a filter. Your task in this example is to use MIDI to control these ADSRs, triggering them and releasing them at the appropriate points. This example uses a number of different classes, each in its own source files, and we looked at those the last time around. In this case, the only code you need to change is inside of render.cpp. Specifically, look at the note on and note off functions for triggering and releasing the ADSRs. And then in the render function, you need to write the code to process the ADSR values following the same sorts of things that we did in lecture 14. Pause the video here. Alright then, here we go. This project is going to combine the ADSR from lecture 14 with MIDI control. We went over the ADSRs in detail in the last lecture, so I'm not going to cover that again. Instead, I'm just going to jump straight to the MIDI control in note on and note off. In the note on function, we have most of the same code that we had before, keeping track of the active notes, converting the note number to a frequency, and mapping the velocity number to an amplitude in decibels. Now remember, of course, that a lot of classic analog synths didn't have amplitude control at all, so you might find that the response is more satisfying just to disable this. The key part of this code is the triggers here. At the end of the note on function, we have to trigger both the amplitude ADSR and the filter ADSR. In the note off function, we then have to figure out when we need to release the ADSRs. Now, it's not necessarily the case that we want to release the ADSR envelopes every time a note off message is received. Remember that we might have multiple keys being held down at a time. Instead, we need to check when a note off is received, have we reduced the number of active notes to 0? Only when that's the case should we release the envelopes. So here inside of this if statement we can call release for both G amplitude ADSR and G filter ADSR. Otherwise, if the active note has changed, we don't necessarily need to do anything at all with the envelope. All we need to do is update the frequency. Inside of the render function, we have a lot of the same code we saw in lecture 14. Once we get down to the for loop, which is processing the audio frames, we can see here what we need to do to process the amplitude ADSR. We need to call its process method once per audio frame. That is ultimately going to give us an amplitude which we're going to scale by the global amplitude being determined by the MIDI velocity. That gives us this variable here, which we'll ultimately use to multiply the output. Likewise, as we saw in lecture 14, we're going to process the filter ADSR to give us a control signal, which we then renormalize to set the frequency of the filter here. That will then be processed in this line of code here. So we can run this and see this in action. Alright, so now we can press some keys. And we hear the ADSR that we had from the last lecture, now controlled from our MIDI keyboard. Now one thing that you might notice here is that every key press produces a new attack on the envelope. That's not necessarily how analog synths work. To understand how synths usually handle this situation, we should go back to lecture 7, where we looked at gates and triggers. Both of these were effectively digital signals, but they behave differently. A gate, in synthesizer terminology, is a signal that has two states, open or closed, on or off. And what we care about with the gate is its ongoing instantaneous value at any given time. The gate, for example, might tell us whether the oscillator is playing or not right now. By contrast, a trigger is also a discrete signal, but it represents an instantaneous event. We typically use triggers to begin envelopes, advance sequencers, and carry out other sorts of instantaneous tasks. When we get a MIDI note on message in our synth, we might want to operate both gates and triggers for that. In this case, the gate should stay open as long as the synth is currently playing. In other words, the gate stays open as long as any keys are held down. However, we don't necessarily want to re-trigger the envelope every time a new key is pressed. What a lot of classic analog synths will do is that the trigger will only happen on the first key press when there was no key previously pressed. When a new key is pressed, there will not be another trigger, but the gate will remain open. What that means is that the frequency of the sound will change, but the amplitude and the filter will stay the same. So that's your final task for this lecture. It's a simple change to make in the MIDI ADSR example, but make it so that the ADSRs only trigger on the first note on received and not on subsequent ones. Pause the video and try it. Okay, here we have the change we needed to make. It's very simple. All we needed to do was put the calls to the trigger methods inside this if statement, so that we only call the trigger methods if exactly one note has been pressed. We can run this and hear the difference. And there we hear a much smoother transition between multiple notes being pressed. And that brings us to the end of this lecture. Thanks very much for following along. Be sure to subscribe to our YouTube channel to be notified of all the new lectures as they become available. Next time, we're going to look further at the MIDI protocol, looking at control change, pitch wheel, and other MIDI messages. In the meantime, you can always reach us on social media, or at our forum, on our blog, or at our knowledge base at learn.bela.io. Thanks very much for following along, and we'll see you again soon.